Hello and welcome to our newest presentation. My name is Konstantin Renkens, and today's topic you can see on the screen. I hopefully share. Today we're talking about metallic 3D printing and the analytical challenges that this involves when using XRF to do testing. And this is mostly data based on a study that we were involved in. And so, let's get right into it and start with a little overview, what we're going to talk about. So, the idea of three-dimensional printing or additive material printing is to have a metal powder and you'd use a machine to print pieces from that powder. So the question was, in terms of a consumable in the future, how do we make sure that the quality of our powder is always the same, and what analytical possibilities do we have to make a quality control of this consumable, the powder? So we'll talk about the powder, we'll talk about how to measure it with handheld systems. We'll talk about the quality of the powder in terms of what it needs to bring and how do we control this. We will talk about the grain size of it, because that is also a topic when it comes to the different machines used for this additive metal printing. And we'll talk about the homogeneity of the printed pieces we make. In our example, we made disc out of the powder. And finally, we'll talk about, FLUXANA's most favorite topic, making a application based on fused beads in order to do quality control. Also, with regards to the future, when we are talking about, this will be a more common process and there will be more powders be available in the future, and you have to have some way to control them and to do quality control of them. And all this in mind with how do we fulfill a specification for a given batch of powder sample that we get. So let's get started with a bit of basics. Just to give us an idea, what are we talking about? There's basically two methods to do this powder bed fusion with laser beam, or you have the short down here. Actually, I have to use this screen, sorry. So the idea basically is that we have a metal powder that we roll onto a surface, and then we use a laser beam to basically weld this or melt this, and we increase the height, or in this case the actual printing surface lowers, so it goes down, and we apply layer by layer, and that way we make a three-dimensional metal piece depending on the program. And the first technique is using laser beam. This is in a protective atmosphere. And there is another technique, which is basically powder bed fusion with electron beam. So we're using a spark. This has to be done in vacuum. That gives the powder we actually need different properties. So if we look at the powder itself, we basically fill our printer with this metal powder, and there are various ones available, and that will be our raw material for the actual printing process. So the question that quickly comes up is, how do we check new batches of powder, or how do we make sure that each time we refill the machine, it is working the same day as before? And also looking at the normal situation with ink printers, how about third-party materials? If we don't want to buy like the batch we usually buy, or the brand we usually buy, or if it's not available anymore, how do we replace it with something similar, and how do we make sure the equipment works the same way? So one thing that was asked is, can we do a quick check of incoming power, a quick raw material control, so to say, by just using a sample cup and a handheld XRF to see if the batch we are getting is the same quality as the last one we used. And do we need more than a standardless package that is on the handheld? Or like the question was, do we need a specific calibration in order to get results that we can use to identify differences in the powder that might cause problems in the process? So this was one of the first questions. Can we make a control of the incoming material of a new bag or a new box of our powder with a handheld? And we did some studies on that. And just to give you an idea of the scope of that study, it was 3 different materials, which were in total 5 powders, 3 for the laser beam and 2 for the electron beam. The one we will be talking about in this presentation is the stainless steel one. Although, yeah, no, sorry. The materials were stainless steel, tool steel, and then an aluminum based and an aluminum alloy. And yeah, our presentation will actually be mostly about the tool steel, just to pick an example. To talk about the differences in these, let's talk about the powders itself before we go into the analytical details. Depending on the technique you are using, laser beam or electron beam, your particle size of the powder will be different. I'm not an expert on this machine, but I can just assume this is depending on how the machine fuse it together. The laser beam is actually finer when we compare it to the particle size of the electron beam. So this one in vacuum here, this one under a protective atmosphere, but yeah, the LB, let's call it that for now, is the finer powder by quite a bit, actually, if you look at the grain size or particle size. So the first question for us, knowing that particle size can play a role in analytic with XRF. We know that from other materials and other samples. The first question for us was, does this matter, or can we use one application, one program for both of these different powder, or do we have to make an individual one, a special one for each of the different powders? And so the first test that we made was we took this stainless steel sample from, like I said, it was 5 total samples, but we took this one with the special specification you can see down here. So that's your typical tool steel. It's iron, nickel, and chrome. And the first test we made was we made a loose powder measurement in your typical sample cup. And as a comparison, we used a pressed pellet where we just, compressed the sample using a binder. The binder we used here was Celeox in this case. And yeah, the first question was, do we need a preparation, a special one, or can we just analyze incoming materials with very little effort? How much effort is required to get a good, reliable analysis? And I'll present you the data in the next sheets, and we will talk a bit about our findings. So in this one, we can see we made the homogeneity test, basically taking different bottles from one of the same charge, and we just looked at the measurements. We used a standardless software for these measurements, and this was one of our wavelengths dispersive XRF machines under helium. So we basically filled it in a cup and measured it standardless. And as you can see, the homogeneity of the powder is really good. That mainly comes from, or the explanation would be that this is an alloy which is homogeneous, and it is prepared in a special way to give us this very specific particle size. So unlike a natural product where you have a lot of more different effects, this one is a homogeneous sample and a very defined particle size, and that explains why even with very little effort, just taking loose powder and measuring, we get a very good reproducibility and a very bad homogeneity in the different bottles of one charge. And this is for the one SAM, the test of homogeneity, pretty good homogeneity in the end. It was the results. We then check this one, the loose powder, and compared it to a pressed pellet. And so what we see here is for all 5 materials, we have the loose powder on top and the pressed pellet, and we use the same standardless software to analyze this on our wavelengths dispersive unit. So standardless meaning we just told the software what this is, and then the software made the analyzers for us, and it's the same program that does the analysis. And as you can see, the differences between the pressed pellet and loose powder are quite small. So in general, what we can do as a conclusion is say there is some systematic systems you can see, but mainly in the small component, and that is based on the calibration itself. The loose powder obviously has a film and so on, so there are a few effects. But generally speaking, we can say that we find a good agreement between the results, and we are also very close to the specification that it should be. So as a result of this test, our idea was, just as a reminder, the first one has a different grain size, but as a conclusion, we can say that loose powder and pressed pellets are both suitable depending on the time and equipment you have. So we can deduct from this that the particle size between the different powders for the different techniques doesn't matter that much, and also the advantage of doing a pressed pellet, which you usually see in the accuracy of results, is not really present here. So both are suitable depending on the time and equipment you have. By equipment, maybe just to sort of clarify, for example, if you don't have the option to do a helium flush in your machine, then obviously loose powder is a bad idea, and you would have to do pressed pellet and vacuum. But yeah, depending on the equipment you have, if you can do both, loose powder will probably give you the same results as a pressed pellet, so you can skip that step. The next step that was made is then to test the homogeneity of the actual product or printing stuff, the actual printed part that we are doing. How homogeneous is this? And to do that, we actually collected data from a different laboratory, and the idea here was that we make this kind of modern art, let's call it, and then we measure it with an optical emission system at various points to see how homogeneous is the actual piece that we are making here. And you can see here as well, if we're making horizontal measurements on this flat surface, we get a very nice homogeneity of the sample. We then measured the 45-degree angle and also the vertical piece. And you know, just looking at the data, it's a lot of numbers. Pause the video here if you want to check it, but the homogeneity is very good of that printed piece. And also, again, we are within the specification of that material. So so to kind of sum up what we've learned so far, let's say, is in order to analyze these materials, there is a few methods available. We can do the standardless method on a just loose powder, so just sample cup, fill it in, measure it, and check. We can also do digestion in ICP. I think we have some results at the end where we compare all 4. But we can also analyze a test body that we make And then finally, yeah, you know, FLUXANA's favorite is obviously to do fusion and XRF, and we did that with a sort of with an idea in mind. The idea being we now have a limited set of samples that are fairly known, also because they are measured with these three different methods, XRF, ICP, and OES. So we basically have five different samples now that are, yeah, standards basically. But what about future material? If this technique is used more, there will be more materials coming in from different sources as well. And obviously, everybody will want to have a method to analyze this. And that is where our fusion idea here came in order to characterize future CRMs, maybe. We need something that is kind of traceable and reliable. So the idea here was to go for a fusion or a way to do this with fusion. So let's have a look how we do that. Generally speaking, well, this is metal powder. So in order to make a fusion, we treat it as an alloy. In this case, we were talking about the tool steel. So that was an iron-based alloy then. And the idea to do fusion here is then to mix our powder sample with an oxidizer, and we do that at a low temperature to get the sample oxidized so it doesn't damage our platinum later on when we do the high temperature fusion. We then mix that oxidized sample with our borate, our fusion, our flux, and yeah, we then do the fusion process in order to get a fused bead. One little side note here, I was involved in the practical part of actually doing a lot of these studies, and what we found is that if the powder comes fine, then that's okay. The fineness of the powder here is very important. If you go above the, I think it was 100 ppm, you get into trouble because of the oxidization not really working. So yeah, some more details. We have 600 degrees for the oxidization, and then we have around about 1200 to 1250 degrees to the fusion. We do have some more, yeah, actually step by step pictures on how the recipe worked. So we put the fusion flux in a crucible, and usually we make a little dent in the middle, and in an extra little container, or we call those ships in Germany. Like this is where we mix our sample with the oxidizer. In this case, that was strontium nitrate, and we used sodium carbonate as a catalyzer. And then, yeah, the sample on top. We mix this in the little ship, and then this gets transferred on top. We don't mix it here in the crucible in order to prevent like the sample from touching the platinum and causing, well, more tear than wear and tear than we need. So we oxidize this. This can be done in a muffle furnace. In this case, we used our fusion machine for this, for samples. And the oxidization is, I think, like 12 minutes. Once this is finished, we let it cool down, and then we add the rest of the flux on top. And then we do the actual fusion. Also in this case, again, on the left, we have our electrical one, but you could potentially also do this with a gas fusion machine. Yeah, the whole idea here is to get a good fused bead, and most importantly, to prevent any damage to the crucible. The problem with metallic powders, you're probably aware of this. There's also, I think, another episode of this series where we talk about it. Platinum is really, yeah, it's dangerous to work with metallic samples in general, and so you have to stick to these procedures to make it work and get your fused beads without damaging the equipment and your platinum wear in the end. You want to use it for as many fusions as possible, so you want to be careful. And yeah, FLUXANA's idea then was with this recipe, we made a calibration set for this stainless steel in this case, but also for the other materials mentioned before. And we made this basically from pure chemicals. So we took a look at the range, and we made these, well, 12 calibration standards just based on pure oxides to get these mixtures. And there is a standard available down here, which was used then. This was actually quite new at that point. It was just came out. So we used this one as a validation sample in order to check how our synthetic calibration hold up. And the calibration, since we are within a very strict matrix, like this is all the same. If you look at the ranges of our standards here, this is a very narrow range. So what we ended up with was a nice correlation and no need for matrix correction. So this is, in this very specific application or method, it is very simple to make a calibration, and you get a very nice fitting, as you can see, very low RMSs across the board, even without any form of matrix correction. So we were just doing base curves here. And yeah, we get some more measurement data here in the end about our sample that we were talking before. And this is now measured with the application that we made from synthetical samples. Yeah, in this case, we have 12 repeats now. And as you can see, it fits quite well within the specification, but also the repeatability is very good, as we would expect from fusion. And yeah, to kind of sum this up then, is as a validation for these results, we then use this validation samples to look at how correct are our results. And yeah, again, there is red numbers here, but don't be confused. This is just to kind of, green and red always sticks out. So red doesn't mean bad here. Red is the certificate value that we have from the documentation, and green is what we get from our repeated preparations here. And yeah, you can see that it matches quite well. So the validation was quite successful. And there is also another one available that we then entered, which is a NIST standard. Again, I think this data was added a bit later because it's pretty new. And also there we could find a good precision, basically. And so in order to compare this, now we can see that the fusion works quite well, and it has a lot of potential. But we also saw that as a intake control, as a control of incoming material, loose powder and pressed pellet were also very promising. And so the next question then was, how do all these three methods that we use with XRF compare? And so what we did was we compared our loose powder method done on a standard law software, in this case wavelengths dispersive unit. So it was the same equipment that we used for the XRF fusion method. And we compared the specification versus the two analysis techniques. And as you can see from the graphics, is that they are both very promising because they're inside the specification. So the method we are using is obviously more time consuming, but it is more traceable as well. While the other one is very good, or is sufficient, let's say, for the measurement of incoming material. It's we were kind of bringing a lot of points together now. But yeah, we did this with a wavelengths dispersive unit and then also with a handheld. And you can see that loose powder compared with the fuse bead, both is very promising in terms of the yeah, the results we're getting. Keep in mind that the loose powders were always done with just the basic standardless software package that came with the equipment. So there is also an option here to optimize that a bit towards your machine. So you could do like a semi-calibrated method again. So to kind of summarize all of this, if we're looking at this example, and it's the same was true for all, we have our 4 options for analytics here. We do just the easy way with XRF. We do XRF standardless loose powder. We do XRF fusion, and then we had, like I said, another participate in this study was ICP and OAS, so that was external. The interesting thing is that the results are all very close. So we did that for multiple samples, and looking at the data here is you can see that it is all a viable option basically. And so the decision for any lab who wants to do analysis on this, it kind of comes down on what equipment is available. You can always kind of shift the accuracy by just adjusting your method, but generally speaking, as a summary, you can just use loose powder and standardless to give to get the first idea about your sample, or to check incoming new materials, new batches of your powder. The particle size in the powder does not really play a huge effect from what we saw in our tests here, which is a surprise because that's quite unusual for XRF. But in this analytical circumstances, and because it's a very homogeneous powder, the particle size effects are not really observable. Let's say they don't really play a role. We can ignore them, and we can use the same application for both different. For both of these powders, the one for the laser beam and the one for the electron beam, even though they have different particle sizes. We can say for sure that the powder, the ones we had, the 4 examples, were very homogeneous, and also the part that we were printing in the end, the result of your printing was also very homogeneous. The development of a melting process or a fusion process is kind of an idea to have a future reference method in case that's needed when you're coming with different materials. And there is also, we had an idea to maybe even get a calibration set for handheld so that you can specify, make it specific to the powder that you want to use. Checking specification of new batches with a handheld is definitely possible. There is it's kind of it's a good option to have one, just so that you can make sure that there is no mix up and so on in your presentation. To finalize, just some thanks to the organizers and participants of this study, and that was it from me. Feel free. Well, I don't think there is another. Usually we end with a preview for the next one, but in this case, I don't think we have a date yet, but there will be more webinars in 2025. Thank you for your attention and have a nice afternoon. Until next time. Bye.